Okay, so now I'm ready for the second part of the video, and this is where we get into the calculus. So the fun begins right here. All right, let me get my pen and then we'll get started on this. Okay, so what we'll be looking at now is the derivative of an inverse function. And we're going to develop that idea. So a couple of things that I want to go over in this diagram below here. The relationship of the slopes of the tangent lines are like this. If you have a function f of x, and you have this point, and the way this is written as a is just some constant, the x value is actually the function value of the inverse, and then you have just some arbitrary a. So if the slope of that tangent line is given as the ratio q over p, then it works like this for the inverse function. So for the inverse function, f inverse of x, at a point that is flip-flopped, notice that the a becomes the x and the inverse becomes the y value. So just pay attention to these 2 points and how they flip-flop. It says the slope of the tangent line is the reciprocal p over q. So that should be logical, and we'll look at some examples to show why this works and everything. So our textbook uses this notation. The derivative of a function is going to be represented by this. So if we have f prime, we're doing the derivative of f, and then we're evaluating that at a point of function value on the inverse. And then the derivative of the inverse function, f inverse of x, we represent it this way. F inverse, put that in parentheses, then you have your derivative prime symbol of a like that. The symbolism on this can be a little tricky and confusing. But once you get the hang of what we're doing and the fact that these tangent lines are reciprocals of each other, I think that will help you quite a bit. All right, so here's a diagram right here. So notice they have, this is f of x. This is our function right here. And then this is the inverse. And this has that same kind of relationship we talked about. It's symmetric about y equals x. And we're just picking some kind of arbitrary points on here. So this point right here, we're representing this with an x and y value. A is just, again, some arbitrary number. And then the inverse of a is your x value. So you're just kind of thinking of x and y right here. And then your slope is a rise over a run. So we're going to say that slope of this tangent line is going to be q over p, since that's a rise over a run. Okay, now if you look at the inverse, well, we know that all points on an inverse are backwards. So if we have f inverse a, comma a, then they're going to go backwards. Okay, so if you look at this, the x and y get flip-flopped, and what happens is the slope becomes a reciprocal. So if you look at this just visually, you have a rise over a run, you're going to end up getting on that p over q. So that diagram will show it pretty well, how though you can see visually how the slopes are going to be reciprocals of each other at any point on that tangent line. It doesn't matter where the point is. If you're here, the slope is going to be the reciprocal of that. See, this is getting steeper. This is getting less steep. So that's pretty rational. Okay, so the other thing I wanted to point out on here is the slope is the derivative evaluated at this x value. Okay, remember, keep in mind this thing right here is really an x value. Okay, and then down here, the slope of the tangent line here is the derivative of the inverse with respect to a. Okay, so you got to make sure that you understand how these values pop in there. Okay. All right, this will start making more sense once we do some examples. So going down at the bottom, this is the formula that I'm going to show you how to develop. And I'm going to use f of x and g of x as my inverses. I think it's a little bit less confusing when you look at it this way. So what we have is if f and x and g of x are inverses, then f prime of x is just the reciprocal of the derivative of g prime of x. And if I do that backwards, the derivative of g is the reciprocal 1 over f prime of x. So I'm going to go through and I'm going to derive that formula. Okay, so to begin with, when I derive this formula, there's one thing that we do know we would know, since these are inverses, we would know basically that g of f of x would be equal to x, because we know if we do a composition of functions, if we do g composed of x of f, we're going to get x, and if we do it in reverse, we'll get that. If we do f composed of g, we'll get x. So see, this is a fact that we know. So what I'm going to do on this is I'm going to take the derivative of both sides of this equation, and watch carefully how I do this. Okay, so I'm going to do this with respect to x. I'm going to do d dx of both sides when I do this. Okay, well, this is a chain rule. Okay, we've learned the chain rule. If you do a derivative of a composition of functions, the big function is this whole thing. So that is going to be g prime of f of x, but then by the chain rule, you also have to multiply by the derivative of what's inside. And what's inside is f of x, so that would be f prime of x. So that's what the derivative of g of f of x would be written like. And then, since the composition is equal to x by definition of an inverse function, we also know the derivative of x would just be equal to 1. So we get this. So now what happens is we have an equation that we can pretty easily solve. I'm going to bring this down. I got g prime of f of x times f prime of x equals 1. And then I can divide this both sides by g prime of f of x, and then I'll get what this formula says, see. Okay, so that'll wipe out. Then we'll do g prime f of x here. And then notice what we get as our result, bringing everything down. We have f prime of x is equal to 1 over g prime of f of x like that. And that's what's given in this formula right here. So I just derived this formula right here. Now, if I do this backwards, I would end up getting this. So, I mean, I could do the same argument. I could do f of g of x, and we know that that's equal to x. If I do the same argument, if I do the derivative of this side, I would get f prime of g of x times the derivative of what's inside. And then if I do the derivative of x, I'd get 1. And then if I want to solve this for g prime of f of x, you know, I can end up getting, these things really are just reciprocals of each other. Okay, so you can develop that. Okay, and if I go through kind of like what I did before, I get this. Okay, with that marking out, so I get this form. I get the derivative g prime of x is equal to 1 over f prime of g of x like that. Okay, so I get the same thing. Okay, that's what I meant to type there, is this. Now this really is true. This is true. Like if you cross-multiplied this, you would get this. So these are true statements. Okay, this is a true statement, and so is this. What I did to get this is really I just did the reciprocal of both sides. I mean, if you look at that, you do the reciprocal of both sides, you get this. Okay, so that's valid. Okay, so what we're going to do is now we're going to look at some specific examples that'll hopefully help you make some sense out of this then. We use this rule when finding an inverse is difficult. Okay, so I'm going to do some examples where finding an inverse is fairly straightforward. So to begin with, let's just look at a line. A linear function's real easy to work with. Okay, so to begin with, they're just going to go through these steps right here. So what I'm going to do is I'm going to do the derivative of this function at x equals 4. Okay, so if I do df over dx, I'm just doing the derivative of that function, which would just be 2. Okay, and it's always going to be 2. Okay, it doesn't matter if x equals 4. I mean, think about that. This is a linear function, so the slope of the tangent line is always going to be 2. Okay, so that's kind of the idea on that then. Okay, now what I'm going to do next here is I'm going to solve this for x. We're not going to find the inverse yet. Okay, I'll do that in a little bit here in part C. I'm just going to solve this for x. So let's go ahead and just take this and solve this for x. So I'm going to do this. I'm going to subtract 5 from both sides, and I can do this in my head. And then I can divide both sides by 2. And then I can write this like this. So I get x equals, that canceling. And you can write this, if you want to, as 1/2 y minus 5. Okay? You don't have to write it that way. You can also just write it as y minus 5 over 2. Okay, now that's not the inverse. That's just taking the function and that's solving it for x. What I'm going to do in part C is I'm going to find the inverse. Okay, so we're going to find the inverse on this part. And again, that's the notation is f inverse of x with the minus 1 on it. So the way you find an inverse is you interchange the variables. So I'm going to do this. I'm going to change y to x, and I'm going to change x to y. Then I'm going to solve this equation for y. So I'm going to subtract 5 from both sides to get this. Okay, then I will divide both sides by 2. Okay, that'll cancel out, so we'll end up getting y equals, and I'm going to write this as 1/2 x minus 5. So I'm going to write that as f inverse of x is equal to 1/2 x minus 5, like that then. Okay, and what I'm going to do is I'm going to show you a couple of ways to do this problem, because ultimately what we're trying to do on this is we're trying to find the derivative of the inverse. Okay, and what we're going to do on this is there's 2 ways to do this. One way to do this is this will just be the reciprocal of df over dx. It's just the reciprocal of the derivative of the function. On a linear function, that's going to give 1/2. So that would be the answer to that then. So you've got the slope of the tangent line of f is 2, so the slope of the tangent line on the inverse is 1/2. The other way you can look at this is, notice right here, you know, if I'll bring this over the side, you have f prime of x equals 1/2 x minus 5. Well, if you multiply this out, your inverse is also a linear function, and its slope of its tangent line is going to be 1/2. Okay, so that's what I want you to see. Now, we're going to graph these things, and I'm just going to use the calculator for accuracy, and it's kind of good. You can graph lines pretty easily without a graphing calculator. But let's go ahead and put these 2 things in. And to start with, let's put in the function was 5 plus 2x. That just means you have a y-intercept of 5 and a slope of 2. And then your inverse function, we could put 0.5 like this in if we want to for 1/2, and then just put in x minus 5, like that. And then I'm going to put, you know, y equals x also like that. And then I'm going to graph that. I'll try it as I'm doing these. I'm going to slide over what I'm putting in the calculator here carefully. So I'm going to put that over there. Okay, so that's what I'm putting in my calculator. Now here's the graph, and this is a standard window, like that. Okay, I just want to point a couple of things out about this graph now. That's not what I meant to do. Let me do that one more time, because I do want to show a couple of things on the graphing calculator. Okay, so what I have is I've got this, and I'm just going to have you graph these things. So first of all, the function in red right here, let me get my graphing calculator back out like this so I can show you what I graphed first. So I graphed in red was 5 plus 2x, okay? So let's just graph that the same way. There's a couple of points on here, and you can go to the table of values is what I'm going to do. So if I go second graph, the y2 that's in red there, those are function values. So I'm just going to pick a few points. Like there's a point 0.5, and I'm going to label that and have you label that. And let's see, another point on here that I see is, let's go into the negative numbers. There's -3, -1. And I'm just going to pick 2 points on here. And then that will be the graph of the function f of x. Okay, now on an inverse, well, all we got to do on an inverse is just flip these points. So you're going to see that 5, 0. See how that shows up? 5, 0 is on the inverse. So I'm going to put that point there. And also -1, -3 is on there. So if you look at that, you got -1, -3. So if I put that, that will go like that. And then I can go through and graph that out like that. Okay, kind of hard to draw a line without it being crooked on this. So that's my inverse like that. And it's symmetrical about that line, y equals x. I'm not going to draw this perfectly, but I want to show you how I can tell I'm right on this calculator. Okay, so I'm going to move this over here, and I'm going to show you what you can do as a quick way to check that you're right. The keystrokes on this for checking are going to go like this. We're going to go second, trace, and then we're going to open up this menu where you have a derivative. So it's option 6 has a derivative dx. Okay, so I'm going to go down and do this, then I'm going to press enter. And what I'm going to do is I'm going to check the answer just on one point. Okay, the problem said find the slope at x equals 4. It doesn't matter. The slope is always going to be 2 on the function. So what I can do is I'm on the function right now. That's f of x is this red graph. And if I just go through and type in 4 on that, see, it's going to give me that the derivative is 2. So that right there is telling me the derivative is 2. All right, when x is 4, the derivative is 2. So we got that right. Now I'm going to repeat this, start over again. Now, and I'm going to go down to this option 6. Now this time, you can kind of scroll between different functions. Okay, and you have to kind of, there's the black one. You have to kind of use up and down. So I'm on the black one right now. So what I'm going to do on that is I'm just going to use the same value because the slope's always going to be the same. So if I just type in 4, I get 0.5. Okay, so when you're doing a linear function, it's pretty easy to see. All right. So what you'll kind of see on this, if I go back to my table of values, I have a 0.413. This is really a 0.413. And on the inverse, you're going to have a 0.134, like that. And on this, the slope is going to be 2, and then the slope on the inverse is 1/2. That's the way it works on a linear function. Okay? Okay, all right. So really, all you had to do on a line, on a linear function, if you got a linear function and you're asked to find the inverse, the derivative of the inverse, as we are down in this part D, then all you got to do is do the reciprocal of that. Now that works on a line. It doesn't work on everything. I mean, the points are going to be a little bit different. They're always going to be reciprocals, but it turns out that every point, not just 4, 13, and 13, 4, have this relationship. It's a little bit different on the next example. Okay, so I'll move to the next example, and we'll run through the same kind of idea on this. This time we're given a quartic function, something to the 4th power. So we're going to run through the same thing here. And yeah, and I meant for this to be x equals 1, so I'm going to have you change this to x equals 1. I need to do that on my note hand. That's just easier to see. So let's work with it this way. Okay, so we're going to go ahead and do the derivative. Okay, we're going to do df over dx. That's just taking the derivative of this function. So 1/2 is a constant. Derivative of x to the 4th is 4x to the 3rd. Derivative of 6 is 0. So we get 2x to the 3rd. And then if we evaluate this derivative at x equals 1, we get 2 times 1 to the 3rd. So we get 2. So we get the same slope that we had on the other problem. It's just a coincidence. Okay, so we have that then. Okay, now before we, get into the, finding the inverse and derivative, let's go ahead and just solve this for x. Okay, so I'm going to take part B. I'm just going to write this as y equals 1/2 x to the 4th minus 6, and I'm going to solve that equation for x. So I'm going to add 6 to both sides. You're welcome to do this in your head. Add 6 or just move the 6 to this side. Then we have 1/2 x to the 4th. Okay, then what I'm going to do is I'm going to multiply both sides by 2. Okay, like that to cancel that out. And then if I multiply that out, I get 2y plus 12 equals x to the 4th. And then what I can do is I can do a 4th root of both sides, like this, 4th root of both sides. So what I get when I solve this for x, I get x equals the 4th root of 2y plus 12. Okay, so that is the answer to part B, just solving that for x. Not really doing anything, we're just solving that for x for now. Okay, now we're going to find the inverse. So when we go down to the next step, we're going to find the inverse. So start off by writing the function as y equals 1/2 x to the 4th minus 6. Interchange your variables, so you're going to get x equals 1/2 y to the 4th minus 6. Now we're going to solve this for y. It's going to look real similar to part B. So I'm going to add 6 to both sides. Okay, like this. Then I'm going to multiply both sides by 2 to get rid of this fraction. So I'm going to do that. Okay, that's going to leave me again with 2x plus 12. So that's going to be equal to y to the 4th. Then I can take the 4th root of both sides. And then that will give me my inverse function on this. So I get y is equal to the 4th root of 2x plus 12. Okay, so that would be what my inverse function is on part C. Okay, now I left off part D. I don't know why I did that on the handout, but I'll fix that. So the next thing we want to do is find the derivative of the inverse at the point 1, negative 5.5. So there's a reason why we're doing that point there on this then. So let me just show you, remember the function f of x, the function I gave you is 1/2 x to the 4th minus 6. F of 1 is equal to 1/2 times 1 to the 4th minus 6. That would be 0.5 minus 6, so that is negative 5.5. So it means on f of x, we have the point 1, negative 5.5. So what we're interested in is what's happening at the point on the inverse. So we're going to be looking at this point right here. So we don't have to really do anything. I'm going to show you 2 ways to do this. But really all we got to do is do the reciprocal 2. Because these points are inverses of each other. One, what we would do at this particular point on the inverse, we would really be working at the point negative 5.51 on the inverse. So on the inverse at that particular point, and I meant to say negative 5.51, it would be equal to 1/2. Okay? So the other thing that you can do on this is I'll show you an alternative. Okay, so I want to show you one other thing. You don't really have to write this down. I just want to show you something. So we have the inverse is equal to, we got really 2x plus 12 to the 1/4 power. That was our answer to part C. If I did the derivative of this inverse, let me show you what would happen. So we have 1/4 2x plus 12, and then subtract 4/4 to the negative 3/4 power times the derivative of what's inside, which is 2. That's a chain rule. So you could reduce 2/4 to 1/2. So we'd have 1/2 times 2x plus 12 to the negative 3/4, like this. Okay, so let me show you what happens if we work with this derivative. Okay, so if I plug in negative 5.5, and I'm just going to do this on the calculator, we have 1/2 times 2 times negative 5.5 plus 12 to the negative 3/4 power. Let me just pull up my calculator and do it this way and show you what happens and show you what answer we get. Okay, so I'm going to put this in 0.5. I'm going to use 0.5 for 1/2, and then I've got 2 times negative 5.5 plus 12, close parentheses, and then raise that to the negative 3/4 power, like that. See, I get 0.5. I get 1/2. Okay, so the question I want to kind of show you is, Well, you would rather do it this way. You would rather just figure out, if you have the point 1, negative 5.5, then if you want to find the value of the derivative at negative 5.51, then you just do the reciprocal. Okay, but yeah, a person could go ahead and get the inverse, do the derivative, and evaluate it at negative 5.5, and you'd get the same thing anyway. Okay, so that's what I'm attempting to show you on that then. Okay, so we're going to do a check on here too with the graphing calculator, kind of like what I did on the last step here. So I'm going to put in the original function. Let me get this down here and get everything kind of erased. Okay, I'm just going to graph the original function. So what I have on this is I have 0.5 x to the fourth, and then minus 6. That will be my function, and I'll just do that in a standard window. So that's what the function looks like. Now we're only doing this for x greater than 0. If you go back and look at the original problem, it says x greater than 0. That's because this is not a one-to-one function. So the way I'm going to put this in my calculator is like this. I'm going to put in parentheses 0.5 x to the fourth, and then minus 6. And then I'm going to put in division symbol, then I'm going to put in this inequality. So there's the test buttons. Go to test, and I'm going to put in greater than or equal to 0. That way, what it does is it only does the part that is one-to-one. Okay, we can do the inverse of this part, not the entire thing like that. Okay, then I'm going to put in the graph of the inverse. The inverse is right here. Okay, so when I do that inverse, I'm going to have, and I'm just going to type this in like this as 2x plus 4. No, not 2x plus 4. 2x plus 12 raised to the 1/4 power. Like that, and I'll get that in, and then we'll see what the graph looks like. And I'm just going to have you sketch a graph on this then. Okay, so we have that, and then I'll show you how to check the graph on this. So let's go ahead and let's just do a look at our table of values, and let's just find a couple of points. We know we have the point 1, negative 5.5. So let's go ahead and let me zoom on this so you can see us a little bit better. 1, negative 5.5. And I'm going to label that point right there. Okay, then on the inverse, we would have negative 5.51. And then maybe we can find one other, decent point on here. Like here's 0, negative 6. Let's just go with that point. So here's 0, negative 6. And then that would mean you would have also a negative 6, 0. And then let's go one other big one that's, here's 2, 2. That's a good point. So that would mean that 2, 2 would also be on the graph of the inverse. Okay, so your points kind of go like this then. Let me go back to the graph. And here's our function. And I'll label that f of x. And then our inverse is going like this. And then I'll label that as f inverse of x like that. So let me show you again how you can check your answer on this, just to tell that you're right. Okay, if you needed to. It's an easy enough problem to not have to check on because the derivative's pretty easy on this. So the idea is, let's go ahead first of all and check the value of the derivative at x equals 1. So again, I'll go second, trace, option 6. You want to make sure you're on the blue graph, which is f of x. Type in a 1, and see there's your slope of 2. So right there it's telling you you have a slope of 2. And there's your point, 1, negative 5.5. So what I want to do is, the graph of the derivative of the inverse was the reciprocal of 2 or a half. If I want to check that, I just go second trace, option 6. This time scroll up to the red graph and put in negative 5.5. Okay, if you put that in, there it is. See, it's 0.5. Okay? And that's what I want you to see on that. That's how you can tell you're right with your calculator. Okay, so I put these graphs up here. This is kind of the key thing I want you to see is the inverse has a slope of 1/2. and then the function itself has a slope of 2. And see how the points are backwards? So that's what you want to look at to verify, and I think that'll help you understand. Okay, so we're going to go to the next page. There's 2 problems I want you to do. Just kind of repeat what I did, see how you do, and then you can check your answer just as soon as you're done. Okay, so to wrap up this second part of the video, you can go ahead and check your answers on here. And the first one, pretty simple. On the first one, the derivative is -3. Okay, now this is a linear function, so that means if you're doing the derivative of the inverse, it doesn't matter what point you're at. That would be the reciprocal. So -3 and -1/3, you can automatically get that. Solving for x, you would have got x equals 4 minus y over 3. And I've been showing you to do the inverse like this, but if you solve for x, all you got to do now is change the variables. So you'd have y equals 4 minus x over 3. So if you want to just solve this for x, then change the variables, you can do it that way if you want to. It doesn't matter. Okay? And that's it. So the other thing is I went ahead and did a graph. Here's the blue one is f of x. The red one is the inverse. And you can pretty well tell this slope on the function is -3, down 3 over 1. And then on the inverse, it's down 1 over 3. So you want to look at that graph and see if that helps you make sense of this. I went ahead and just did this on the graphing calculator too. So notice that if I look at the derivative at x equals 3, I'm going to get -3. That's going to verify that. Then if I do the derivative on the inverse with my calculator, that gives me -1/3. It just gives it in a decimal form like that. All right. Okay, the next one, problem number 2. To start with, let's see, we're doing, and I think I forgot about this D on the original handout, but I put that on the new handout I fixed. So what we have is the function x³ minus 2. So part 1, we do the derivative, that's 3x squared. Plug in the 1, you get a slope this time of 3. Okay, now what I did on this is you want to notice on here that if f of x is equal to x³ minus 2, if you do f of 1, you're going to get 1³ minus 2, which is -1. So f of x is going to contain the point 1, -1. So f inverse, you should have the reciprocal slope at the point -1, 1. So that's why I'm asking at that particular point then. Okay, I solve for x. You get x equals cube root of y plus 2. If you want to just bypass what I was doing on part C and change this to y, and then that x to y, you get your inverse, which is y equals cube root of x plus 2. And then if the derivative at x equals 1 of the function is 3 at the point, and that's the point 1, -1, then the derivative of the inverse at -1, 1 would be the reciprocal, or 1/3. Okay, and you can kind of see what I did on my graph. I just did this on my calculator. The key thing, notice that at the point 1, -1, the slope of the tangent line was 3. And then notice on this one, at the point -1, 1 on the inverse, then the slope was 1/3. So it just comes out in a decimal form like that. So I think the graphing calculator should really, really help you understand this. I think it's real abstract without seeing this visually. Okay, so that will end the second part of the video. The third part will work a little bit more with some of these examples. It'll be a little bit shorter, I think. Okay, good luck. Cheers.